Hi, I'm Isaac Robinson. I'm machine learning engineer at Roboflow, and I'm going to talk about our new state-of-the-art model, RF-DETR, which stands for Roboflow DETR. Yeah, so RF-DETR is our new object detector. It's built on top of the DETR framework of models as opposed to the YOLO framework. DETR is a family of object detectors designed to take advantage of the transformer architecture, which is what's commonly used in large language models and things like that nowadays. The DETR family is much more recent than the YOLO family. It was introduced by Facebook in 2020, whereas the YOLOs were introduced in 2015. And so it hasn't, had as much time to mature as their family. But just in the past year, we've started to see real-time DETRs come out that are competitive with YOLOs on real-time tasks. And we decided that that's the direction we think object detectors should go in the future and decided to build our own. So we built RF-DETR to transfer extremely well to real world and small data sets. We introduced a new benchmark for this task comprised of 100 smaller data sets. And we show top results on that. We've so far shipped two sizes of RF-DETR, a base size and a large size. The base size runs at 160 FPS on a T4 and is comparable in speed to YOLO M. And the large size runs at about 150 50 FPS. The RF-DETR model is designed to facilitate speed trade-off accuracy adjustments after training. So you can run it at a smaller or higher resolution after training and get different latency trade-offs if you want. So one part of what went into this work was a question about how should we benchmark new models. Traditionally, people have benchmarked these object detectors on COCO, which is benchmark from 2017, 160,000 images, very, very famous and arguably very saturated. People have been working on this one benchmark for almost a decade, and we've gotten very, very good at it. But it doesn't necessarily, many of these papers don't actually test the assumption that their model transfers well to small data sets and different domains. So we introduced RF100. A few years ago, we introduced the dataset RF100. We've updated it RF100 VL to facilitate comparison between large language models and few-shot models with the supervised models that everyone is using. And we think that instead of optimizing for COCO, people should optimize for actual transfer, which means training 100 different models on each of these data sets and evaluating them. It doesn't take more compute. RF100 VL is a similar number of images as COCO. So to benchmark an RF100 VL is not more expensive and should be more useful for real world. So here are our basic results. We see that we are notably missing a small model, which we are working on. But if we ignore that section of the graph, we see that we are competitive with the best models on COCO and significantly stronger than all benchmarked models on RF100 VL. Notably, the improvement that you see between YOLO nano sizes and YOLO medium sizes is similar in magnitude to the improvement you see between YOLO medium sizes and RF-DETR medium, and the model runs at the same speed. We were very proud of that. We benchmarked Define, which is the current SOTA on COCO, and we were not able to produce meaningful results with their open source training code. So we have an issue open in the repo asking them for help. We've noticed that many other people also have had a similar experience. It goes to show models that train on COCO don't necessarily transfer to real world data sets. We also see that YOLO 11 outperforms YOLO V8 on COCO, but underperforms on real world data. The big key here is that we have better pre-trained model. So we start with the Dino V2 backbone from Meta, and it has a lot of knowledge already. So here we can see that by default, it is able to find and segment out this dog without explicit training as to what a dog is. Using that type of knowledge combined with the state of the art in DETR-based object detectors, we present RF-DETR.
Hi everyone. Yeah, so today I'm going to talk about how we actually can train a model and deploy a computer vision application within minutes using Roboflow Instant, a new model we released a few weeks ago. So the goal here is to shorten the time to testing and getting to deployment, getting your computer vision application to production, because right now it takes a lot of work and it also takes a lot of time. For example, the first step is you need to capture data, and the data you need to annotate it, which means adding some ground truth to the images. You need to label it. You need at least like 50 images to get started with traditional model architectures. Then you need to process the data, and I think we work hard on making this process very easy and streamlining it on Roboflow. So that's already kind of fast, but for training a model, you just need to be patient. You will kick off a training job. Depending on the size of your data set, it will take like an hour. It might even take a few days. And then you get to deployment. And yeah, with Roboflow, we also try to streamline that and provide you many different ways of deploying your model with ease, maybe a local deployment or deploying in the cloud with built-in auto-scaling. So how can we speed up this process? This is where Roboflow Instant comes into play. And we want to especially improve the time to label and improve the time or decrease the time you need to train a model. And how can we do that? So Roboflow Instant is a few-shot object detection model. This means the model is actually not trained, but rather prompted with examples. You can see it here on my right-hand side. You can label one example in the image, for example, this apple here. And when you are using a traditional architecture, you would need to label a lot of images and label all the objects in the image. Here, you can label one apple, and the model is already able to understand the concept of an apple, and you can use it to predict on the rest of the image. As you can see on the right-hand side, where all the other apples are predicted by just looking at that one sample. So the cool thing here is it requires very little data to get started. For example, like you just need one bounding box, and you also skip the training time. So you can get to deployment right away, and then get your model and your application to production, and then work backwards, use some active learning, and improve your model over time. Training your model is never finished. You always want to improve it, but this is a great first step to get started. And now I'm going to show you how this actually works. And the data I'm going to use will be some chicken production line data. So you can see here we have some brown and some white eggs, and I'm going to upload the training data here, consisting of 4 images. If we want, we could also add some images from Roboflow Universe and extend the data set. But for now, I'm just going to use this data. Once the images are uploaded, I'm going to start manually labeling them. And as you can imagine, this would be a lot of work. So as you can see here, we have around 200 different sorts of eggs. And what I'm going to do, I'm going to label one instance of an egg, for example, right here. I'm going to call that a white egg, because I'm actually interested in the difference between white and brown eggs. So the next thing I'm going to do, I'm going to label a brown egg, saving that, and maybe adding another example just to be sure, maybe even here, adding another white egg. And with that, we're going to make use of Roboflow Instant the first time. We have here our box prompting feature, which basically uses the same technology as Roboflow Instant under the hood. And as you can see, we're already getting some predictions. By looking at that, the model was already able to understand the concept between a white and a brown egg. And from what I can see so far, this looks pretty good. So I'm going to approve that predictions. I can go here and check how the model would perform on a second image. I think that also looks pretty good. Just checking if I'm missing anything, but it looks good so far. So I'm gonna approve all of that predictions. I'm gonna go back and yeah, from another data set already had 2 more images labeled. Doesn't play a role right now. So I'm just gonna add those images to the data set. And what just happened is the first time you add images to the data set in a new project, we are triggering a Roboflow Instant training for you automatically. If you want to repeat that in the future, you can just train a new model on new images in the data set here. Next thing I'm going to do, I'm gonna click on Detect, Count, and Visualize, which is a template that helps me get started with workflows, our no-code, low-code solution builder. So I can easily count the number of white and brown eggs within the image, which is like my ultimate goal here. First thing I'm going to do, I'm going to delete the label visualization, because when you have a lot of predictions, they are blocking the image and you cannot really see the output. And we would get a count here, like it would give us a count of the total number of eggs. But what I actually want is I want to extract the class name here, and I want to count the number of unique items. So I want to understand how many brown eggs are in an image and how many white eggs. So I'm going to use a test image, which the model hasn't seen before. And I'm going to run the workflow on it. And what you can see here is we got the output image, which looks like that. We can see here the red bounding box indicating the class for the white egg and the blue bounding box indicating the brown egg. So that looks really cool. And we also got the count of white eggs and the count of brown eggs, all within minutes. And the cool thing about this is this logic and these models are already deployed for you. So you can either use our hosted API with HTTP requests or use the Python SDK, run it on an image or on a video locally. And yeah, so that's it from my side. And yeah, thanks for listening.
Hey guys, I'm Bruno. I'm a full stack engineer here at Roboflow, and today I want to talk a little bit about our new Polygon Zone tool inside of workflows. So let me just screen my slideshow. So here's the thing. Usually when we're working with object detection, we're not just interested in the detection themselves. We want to know how they relate to the environment, like whether, like how many, for instance, how many eggs are crossing a specific line, or how many pieces are crossing an assembly line, or if people are stopped or cars are parked in a specific area of the screen we have on a camera screen or something like that. And so what we did is we built this tool that lets you build all of this logic inside of workflows by just grabbing an example image, like say a frame from the stream that you're going to be collecting on and running inference on top, and dragging this image to the workflows inside of the actual workflow tool, and just annotating on top of it, drawing specific zones of interest, drawing lines, whether if you're doing like line crossing, and then just building a workflow that's capable of creating some logic on top of those specific zones and lines. I wanted to quickly show how it works, because I think it's going to be much easier to grasp it. What I have here is a very simple workflow, which is just doing object detection. It's doing some byte tracking, so it can keep track of objects across frames in a video, and it's giving us like a bounding box and label. I have a simple script here, which is basically what you get with the deploy script, and I'm going to run that. All right, so here we have a video that I have saved locally, which is just an intersection, and we can already see some cars and some people on the streets, but we have no logic on top of it. We're just detecting the objects and showing them. So the first thing that I wanted to do is come here after the byte tracker, and I wanted to add a line crossing block, line counter rather. And here you can see that it's asking us to define a polygon zone. And what I can do is I can drag an image, say for instance, a frame of a video, but one of the things that I can do is I can actually select the video, and it's going to automatically grab the first frame of the video. Usually we're doing like still cameras. So this gives you already say the placement of the assembly line or whatever it is that you're detecting on top. And let's just draw a quick line here to count the number of cars that are crossing this specific strip. I'm going to grab this coordinates because I want to add a visualization on top of it. I'll use the same coordinates. Here we're referencing the objects that are coming in this line. I'm also going to reference the objects going out. I don't think we're going to use them, but and then we have the bounding box drawn on top of the line counter and so on and so forth. So let me just save this and run it again. Okay, so we can see that we already have the line here, exactly where I draw it, and it's doing the counting of the objects crossing. I did something wrong with the bounding box line counter. Let's grab the image. Oh, all right. Anyway, so the other thing that I wanted to do is add what's called a time and zone block. And this allows me to draw a zone. It's going to see which detections are inside of this box and give me the detections that are inside of the box and the time they've been inside of the box for. And so you can see that's already giving me the first frame because I'm already working on this video. So I'm just going to draw on this crosswalk here. All right. This should actually be taking detections from the byte tracker. And I'm going to output those. Let's say I have I'll call this in zone. And I'm going to take the opportunity to grab the line counter detections. We can see that in the line counter, we have some properties like how many objects came in, how many objects are coming out. I actually want the detections that are coming in each frame that they do come in. So let's just do line crossing. All right, so I have some properties here and I can save this workflow. What I'm going to do is I'm going to grab my Python script here and I'm going to change one thing. I'll get the line crossings here. And since these are supervision detections, I can actually get the classes by just getting the data property. And we have a class name. We'll get an empty dictionary in case I don't have any detections. I'll do the same for the zones. So this should be the objects that cross the lines. This should be the classes of objects that are inside of the zone that I draw. And to see, let's say we want to do some form of alerting. If a car is coming and we have people in the crosswalk, all we had to do here is do something like if car in line crossing and person in zone, then let's just say print alert. All right. Okay, so since I drew sort of a small crosswalk, we're not seeing anything happen here. Let's just say we have to change this. This should be as easy as grabbing the workflow that we have defined, saying we want to change the time zone block. So I click on set polygon zone. I can actually edit this. So I could stretch it out a little bit. I could actually clear it, set a new image here, but it's super easy to work on these polygons. It already updates the coordinates. All I have to do is hit save. And the next time I run the workflow, it should already be looking at the new references for the coordinates. And you can see here we have like first alert of a car crossing because the person's actually on the sidewalk, another car crossing, another alert. And this should give us the opportunity to do all kinds of things regarding like detecting people when there's like vehicles coming or doing any kind of spatial logic with our detections. And as you can see, editing this stuff is as easy as grabbing here, changing, hitting save, and the workflows is already deployed and ready to go on the next one. And that's it for the Polygon Zone editor inside of workflows. Thank you, guys.
So right now in workflows, we have a number of different integrations to basically take the output of your workflow and integrate it with systems in the real world. So that includes things like ERP integrations or MES integrations. We have OPC UA, MQTT, and various other integrations. And so really, the Microsoft SQL Server block represents one more way that you can integrate your workflow with your systems. So for those who are unfamiliar, Microsoft SQL Server is basically a database created by Microsoft. It's used by a lot of really large enterprises. So at Roboflow, we see that with manufacturing companies or healthcare companies. And oftentimes these databases store all sorts of different data and are integrating with their ERP or their WMS or whatever it is. So I'll basically walk through the process now of how you can include the Microsoft SQL Server block in a workflow. So we start, of course, with the input block in the workflow. Next up, we got the object detection model or whatever model you're going to be running. So that's going to be the one that's trained within Roboflow. Next one that I'll throw in there is the continue if block. And that's basically going to create a conditional that allows us to determine whether or not to send the output from the object detection model to a Microsoft SQL Server block. Next, we're going to have the Microsoft SQL Server block itself. There's a handful of different configurations that go into this block. So that includes things like the username and password, if credentials are set up for the database instance. It can also be things like the port and IP address. So those are all completely configurable in workflows, and you can edit that within the UI. And then lastly, of course, we have the output. So here's an example payload to the Microsoft SQL Server block. So I think roughly as you would expect, we have the columns represented as keys in this array, and then the values of each key represent the values in a row within the table for Microsoft SQL Server. Cool, so that's just a very quick look at the Microsoft SQL Server block.
Hello everyone, my name is Pavel and today I'll be talking about building a visual search engine with batch processing. Before moving on, let's take a look what visual search actually is. Long story short, that's a piece of technology that lets you ask questions in natural language, namely plain English, and receive images back that are relevant for your query. Let's take a look on the very specific example of visual search usage. Let's assume that we have a directory of images and we don't know anything about those images apart from their existence. In particular, we don't have any descriptions of the images and we don't know about the locations where the photos were taken. But we have a particular problem. We would like to find out which photos were taken in Paris. So having visual search system employed into the work, we could simply ask this question in English, and we can expect that search engine with its capabilities would be able to filter out the data that are relevant for the query we have just submitted. That's cool, but let's discuss what are the practical applications for visual search systems. If you're running e-commerce, you may want to suggest your customers images that are like products that are similar to another products that they were looking for in the past. If you are running inventory management system, you may want to localize the items in a warehouse based on other reference images that employees of the warehouse may be taking on the daily basis to locate the products. If you're running quality control use cases, you may want to find defects in the products in your manufacturing lines. And why at the very end of the day visual search is also very impressive is the fact that it's very easy to kick off and integrate within already existing systems because search capabilities are already present. They are first-class citizens of many production-grade systems already, and visual search is just a step forward, an evolution of that primary search capabilities that we all know and use and on the daily basis. What's also nice is that you may not really need to train a custom model to have your system up and running, and even if you do, with growing number of images of your dataset, you may not be in need to retrain your models over and over when new visual phenomena are captured in the new images that you are adding into the dataset. And what's also nice, like visual search systems usually very effectively scales into millions of images and can be built with open source tools, which I'm going to prove in a moment. Let's see what I have built to just showcase the potential of visual search. I've created simple web app that you can see here in my browser, which is going to be able to retrieve images that are relevant to the queries I'll be prompting in this search box. And I have built an index of images on top of a directory of images that I have prepared with 50,000 of different images scrapped from the internet. So I don't really know what's there, what's inside of this dataset. So let's try to run some exploratory analysis to see what we can find out. So recently I was visiting London, so let's see how London looks by night. I'm just like typing the query, and in a matter of seconds, I'm getting very reasonable results based on the query I have just submitted. We may try a different one, for instance, wild nature, and you can see that I'm given in the response quite nice pictures. I can provide much more specifics into the queries that I'm submitting. So I'm just typing during winter, and now we should be able to see winter photos of wild nature. If you like, I don't know, dogs, you may also find dogs here. If you want dogs and kittens, that should also not be a problem whatsoever. Although, from what I see, those images are actually not showing cats, but rather like different animals. So you see, like, these visual search capabilities are really nice. They scale really well, but sometimes, especially when the data set is not filled with the data that you are looking for, you may be getting results that are somewhat relevant, but not perfectly matching what you are going to look for. What's also cool that I'm not only able to run queries with text, but also search through other images. So if I submit a reference image here, I'm going to get very similar responses back. In this particular case, that's probably St. Peterplatz in Vatican City. So I'm going to see a lot of buildings from Italy as a relevant matches. So now seeing that demo, you may be wondering, how could I build this? In fact, that was very, very easy, utilizing open source tools, both the ones that we have built at Roboflow and other that are built by external parties, for instance, by Facebook AI team that released Facebook AI similarity search library that we are also using to build that demo. The most challenging part of this, especially at scale, is building the index of the images that requires computing so-called embeddings. Recently at Roboflow, we have released batch processing capabilities, batch processing feature that can be used to obtain such index. And let me share with you how easy it is to build such index. We start from creating the workflow that is going to simply calculate the clip embeddings. The embeddings would be the core fundamental things that we need to place into our image index. And we have this nice UI that would allow us to spin up batch processing job that we simply point the workflow that we want to use. We can drag and drop images that we want to process. We hit the create batch job button. After a while, our images will be submitted and new batch job will be triggered. We need to wait a couple more seconds for this upload bar to finish. And once this is done, we are going to see a new entry in this table here, indicating that our new job just started. I have already pre-computed couple of similar jobs just to show you. So at the very end of the day, you would be able to pull the results back. And once you do it, you will be able to build the index of images that is powering the application I was showcasing just a moment ago.
My name is Sachin. I'm the infra lead at Roboflow. And today we're going to be talking about serverless hosted API v2. So we've been chatting about new models, Roboflow Instant, new ways of building workflows, and very creative ways of using ML or machine vision in your projects. But then the problem that I want to dive into a bit is after we've got that AI model and we've built our multi-step workflow automation, how are we going to deploy this and actually use that amazing work we've done with creating our models and our workflows? So there are two options, basically, if you look at it from a deployment perspective. You can either run the model in the cloud, hosted by Roboflow, for example. We have many hosted solutions. Or you can do self-hosting, run it on your preferred cloud platform, or if you have edge devices in your hardware. So in this webinar presentation, we're going to look at one of these new options that we've added to Roboflow to let us host and deploy and serve your models and your workflows. So what we're talking about is serverless hosted API v2. And well, actually it says beta, but I have some big news for you in the next slide. And let's compare it with the serverless hosted API v1, which is the current state of the art in Roboflow when it comes to serverless model hosting. So what we're doing with v2 is that we are adding the ability to take advantage of GPUs while doing inference. And because we have GPUs, we can support a whole lot of models which otherwise are hard to infer on CPUs only. And we've also learned that the world's moving on to bigger images and higher resolutions. So we are offering flexible and larger image sizes. And as you can imagine, since we are putting in more hardware behind the model through these GPUs and better servers, the execution latency is lower as compared to our v1 API out there. And there are a few more differences. I will flash the documentation page during this presentation, and then we'll share the link with you guys. But let's go. So we have this hosted serverless API v2. It's beta right now, and it helps you deploy quickly, scale up easily. And of course, since it's serverless, you're not paying for the server when you're not doing any inferences. So it's usually a huge cost saving. And today, we're actually removing the beta tag, and this becomes generally available in our platform. So let's see it in action. So let me exit from the slideshow, and one sec. So the way we'll start this off is let's just take a very simple workflow built in Roboflow. So this is just a YOLO world model. It's a zero-shot object detection, basically. And what I've told this model is look for persons, basically, right? And glasses, but we'll focus on persons. So I click on test the workflow. And before I do that, so this is the change. So you could run it on our hosted API, which is v1, the stuff we've had for the past 4 or 5 years, and it's not going away right now. So nothing's changing if that's what you like to run. However, you can now choose the serverless hosted API v2. And all that changes is basically the URL to which we are sending the inference or the workflow execution run. So we will click on connect. And you see this green tick box means it's connected to this backend. And then let's do a test. Let's select a file. I have a file. I'll show you what's in it. It's just a bunch of people sitting around in a hall. And we want to detect some of those people, right? So that's what we want to do in this workflow. So I'm going to click on run. And it's thinking, and you've already got the result. And we can visually look at it. And you can see it's marked out many of the people in that picture. Of course, the focus is on, for this talk is more on the serverless v2 API. So I wanted to quickly show you guys the documentation, and we'll share the link in the chat, maybe. And so I just showed you that, you can point the workflow to infer on the serverless hosted API v2. And then this has got some descriptions. It has some more of how it works. But so what we've changed really from an end user perspective is that we've improved the hardware on the back end, right, to support the GPUs, and which means that the execution time reduces, right? And why is this relevant? So let's look at a few of the benchmarks here. So V2 is the new one, and V1 is the current one. And so now, from our networking 101 days, we remember that when you're trying to send a request to a server and get back, make it do some work and get it back, there's lots of different types of latencies involved. So there's a latency involved to send the image to the server first, depending on where you are in the world and how much latency or bandwidth you have. And of course, remember here, you might be uploading big images. So this is the network upload time, right? And that doesn't change. That's just a function of the geography. Then, of course, if the service is really busy or something, you might have a little bit of queuing time, although we work on optimizing this to a minimum. And then there's the execution time itself, which is how much work did you ask the server to do. Depending on that, you will spend time, while your model or your workflow is processing in there. And then after it's done, it has to send that response back to you, right? And then again, it's going over the network. Again, you might not have full control over it, but that is also a part of the end-to-end latency that's seen by the client between when they started their request and when they actually got back the answer from their workflow or their model. So, but here, what we've been able to hack is the execution times, right? And these are representative. Actually, they're based on the COCO models for these. In this case, it's the YOLO 8s, and the X, M, and N are respectively extra large, medium, and nano, I believe. So different sizes of the model. And also the 640 is smaller images used in the test, and 1280 is higher resolution, right? And here you can see the time taken for the execution, right? V2 is that GPU enabled the new endpoint we've created. And V1 is what we've had, and it's still there, but you can see there's a huge difference in the execution times here, right? So that's what we've tried to improve for our product. And you can see there's a big difference, especially for the larger models and when the resolutions are higher on the images. There is a huge difference in the execution time. And so that is the key improvement that we are bringing with this V2 of the serverless API.